Welcome, and thanks for joining the SUSECON Digital session. My name is Jan, and I'm a software engineer in SUSE's Enterprise Storage team, where I have the good fortune to work on Ceph and its ecosystem on a daily basis. This talk will be about, surprise, surprise, software-defined storage. While software-defined storage is a great tool for deploying scalable and highly available storage that offers a high degree of flexibility, the trade-offs inherent to this flexibility are not always obvious. In this session, I will attempt to highlight fundamental trade-offs and illustrate them with real-world examples, so that hopefully software-defined storage becomes more transparent and predictable. So let's have a look at our agenda. First, I'll need to cover a quick disclaimer, because it always depends, and with complex topics, context is everything. After this, we will take a quick look at Ceph and its building blocks that are relevant for us today. Then I will try to highlight some of the trade-offs inherent to Ceph in particular and software-defined storage in general. Last but not least, we will look at some concrete pitfalls that can be caused by these not so obvious trade-offs and some that are independent of them, and maybe how to avoid them. So as for a disclaimer, I'm a software engineer, and software engineers are rarely experienced real-world operators of the software that they build. They do, however, tend to have a good understanding of the underlying system and its theory. What you will hear in this presentation might very well clash with realities that you, as someone operating and planning Ceph clusters, face on a daily basis. So consider these things I lay out here as guidelines, maybe points to consider hopefully as early as possible in the planning phase, not so much as a blueprint on how to design or operate a cluster. And lastly, the thoughts I present here are, they're not science or thought through with scientific rigor. They're purely based on anecdotal experience and my understanding of a complex system. Alright, so let's cover some fundamentals, so we're talking about the same things. And also because no talk about SUSE Enterprise Storage or Ceph would be complete without showing the following picture. We are of course talking about Ceph, and I'm sure many of you have seen this picture. For those of you who are less familiar with Ceph's architecture, Ceph is a distributed storage engine that offers client access through object, block, and file access. Internally, Ceph stores data in a distributed object store called Tradeoffs, or the Reliable Autonomic Distributed Object Store. Tradeoffs itself consists of mostly three types of daemons that run distributed across a network cluster of machines. These daemons are the monitors, or mons, the managers, and the OSDs, or object storage daemons. The first two are mainly concerned with keeping consistent cluster state and offering a user interface to set or get the state or particular config variables. Whereas the OSDs are simply there to store the actual data. A fourth daemon that you might encounter in a Ceph cluster are MDS daemons. However, I left these out in this talk because they're only needed for CephFS. I would like to highlight two things here. The fact that Tradeoffs is distributed, so networking plays an important role in its operation, and the fact that Tradeoffs is, at least to a degree, autonomous. The reliable in the name, sometimes it's also quoted wrongly as replicated, implies this, but I have not actually mentioned that explicitly yet. Tradeoffs replicates data for safety. So, should there be any failure in the cluster, for example, say a failed disk or, a whole node going down, Tradeoffs can and will detect this, and it will attempt to recreate the lost data without further interaction by the operator on a different or in a different location. The second important concept in Ceph that I'd like to highlight here is crush, or an algorithm for controlled, scalable decentralized placement of replicated data. So one fundamental problem that distributed storage systems need to solve is, where does the data actually go? For Ceph, or more specifically for Tradeoffs, Crush solves exactly this problem. And the beauty of this algorithm is that data placement solely depends on the data itself. This is achieved through a technique called rendezvous hashing, which is a specialized form of consistent distributed hashing. And it means that any cluster member running the Crush algorithm for any particular data item will get the same result, that is, the same location. There is no need for any communication or central authority. That's at least the theory. In reality, there are other parameters to Crush, namely the Crush map and the current cluster state. The Crush map changes, not very frequently, and in Ceph's case, the Crush map is distributed through the cluster state. The cluster state is, of course, maintained globally consistent for every cluster members by the Mon daemons, as I hinted at the previous slide. Crush maps themselves are an extension to the placement algorithm that provide a user interface for A, specifying cluster topology, and B, specifying constraints for data placement. This allows, for example, to ensure that 3 replicas are always distributed across 3 fire compartments in a data center, independent of the node count in these fire compartments. So with these fundamentals out of the way, let's start looking at, hopefully some more interesting content. Unfortunately, moving to software-defined storage isn't, always all rainbows and ice cream. The benefits and flexibilities involve trade-offs, and some of these are quite obvious and, not new at all, like replication causing storage overhead. Others might not be quite so obvious, so let's try to highlight a few of those. I'll start with the painfully obvious and trivial. The most abstract trade-off when one wants to build a storage system, or let's say storage ability, is that you have to spend money, or you have to trade off money. And before anybody gets a headache from rolling their eyes too hard, let's maybe quickly refine that quite a bit. So when money is spent on a distributed storage system, or actually any storage system, a large portion of that money goes into hardware. The things that are interesting to us here are nodes, or just plain old servers, the drives in those nodes, and the network infrastructure connecting these nodes together. On the hardware side, in terms of storage, no, not on the hardware side, on the other side, in terms of storage ability, depending on the hardware, one gets a certain amount of usable capacity and hopefully some availability guarantees that work well for us. We also get some safety guarantees, of course, though I left this part grayed out, since data safety is certainly not something that you want to actively trade off for other properties of the system. And also, Ceph will always favor safety and consistency over availability and also performance. However, it needs to be on this slide because the safety aspect can certainly be impacted by other trade-offs that we can make. Okay, so to make things a bit clearer, let's look at still abstract examples, but at least examples. So let's consider this abstract cluster where we spend a set amount of money on hardware on the right side. And in exchange, we get a certain ability to store data, like, kind of like detailed in the slide before. So if we now spend a bit more money on, say, additional nodes, we get more usable capacity because these nodes have additional drives in them. But we also potentially improve our availability guarantees. The latter largely depends on our crush map design and which constraints we apply to data distribution rules. However, it is important to note here that an operator gets a say in the weights of these trade-offs. It is entirely possible to trade off the additional nodes solely for additional capacity or solely for improved availability guarantees by, say, adding an additional replica. Another example would be to increase the initial expenditure for better network hardware, say 25 gigabit technology instead of 10 gigabits. Here one can argue that due to the increased network interconnect speed, we improve availability since Ceph is able to re-replicate data much faster. Or in other words, the likelihood of encountering a second node failure is much lower since we spend less time with a reduced replica count. The same argument can be made for the safety aspect, of course. Trading off availability and safety in this case is much harder to reason about, though, at least in an abstract fashion, though it would certainly be possible. And as I hinted at before, in the world of software-defined storage, this is only one side of the equation. I mentioned that we also gain flexibility in influencing replication and thus availability. So let's illustrate this with some nice knobs that one gets to push to influence the properties of the resulting system. So we shove our system over to the right, ignoring for the moment the expenditure on hardware, and add two properties that we like to put constraints on. For our purpose, I chose capacity and availability requirements that we can add to our system. The capacity lever is straightforward to understand and certainly not new or anything. The cluster needs to be able to store a certain amount of data to be useful to a user. The availability lever is also not new, but one can argue it's much more powerful in a software-defined storage context. Replicating data for availability is a tried and trusted technique, but in Ceph we can specify the properties of this replication to a much greater degree. For example, an operator can set up a cluster so that it distributes data across several racks, i.e., the loss of a full rack could be tolerated without service interruption. This, however, has implications for our total usable capacity, which seems to be a less obvious trade-off, at least judging by experience. So as a more concrete example, say our cluster has a requirement to be able to store 80% of the available capacity worth of data. This will negatively impact the resulting availability of a cluster simply because Ceph will run out of capacity when it tries to re-replicate data from failed components, at least at some point. The system could even stop serving I/O in order to preserve basic safety guarantees. So our capacity requirement has limited our range of achievable availability under the presence of failure. We could, of course, remedy this by buying additional hardware to increase capacity. So if we now add back the third side of these trade-off participants, I'm sure you can imagine that there's quite a complex network of interactions that can take one by surprise. In any case, my goal here is not to develop an abstract theory of these interactions and how they work, and I kind of doubt that is possible in a generic fashion. But rather, I want to improve awareness so that concrete real-world clusters can be planned more efficiently and that the resulting systems exhibit less surprises for the operator. So, enough with this rather informal theory foundation. Let's look at examples that are inspired by real-world experiences. A common reason for outages is a misunderstanding how usable capacity and availability guarantees interact. Or simply put, the answer to the question, when is the cluster actually full? Ceph itself has some last resort limits configured. So the health status will go into warn if I believe any OSD is over 85% capacity, and it will actually, this OSD will actually stop serving I/O if it's over 90% full. This is just a safeguard to provide a fighting chance if the cluster ever runs this full. So you should never actually run it this full. However, the trouble actually starts much earlier. So Ceph is typically used in scenarios where component failures should really not impact availability very much. The question is rather which components should be allowed to fail and how many of these failures should be tolerated while still staying available. The example on the slide is, maybe on the extreme end a little bit. However, it's still valid. If the availability requirement is that the cluster should be able to tolerate an outage of 1 out of 4 fire compartments with, multiple nodes per fire compartment, then this has implications for the usable capacity. Or in other words, the cluster should be considered full long before it has reached its available capacity. Otherwise, Ceph will lack the capacity to repair the desired state and be in health warn, or in the worst case, fill up the remaining space to a point where it stops serving I/O. And while this example may seem a bit contrived, I have seen clusters that could not even tolerate a single node failure due to just simply a lack of capacity, and that's really not what you want. A related topic are failure domains and crush maps. As mentioned before, they're a great tool to encode safety and availability expectations into your cluster. So when you define failure scenarios and availability requirements, you also need to think about cascading failures of smaller components. So let's look at yet another somewhat contrived example. You want Ceph to keep 3 replicas, and you set the requirement that 1 full node failure is to be tolerated, i.e. that the 3 replicas must be spread out over at least 3 nodes. So you do the math, you plan your crush map, and you come up with a 3-node cluster because, that does what you want and the price point is pretty unbeatable. So now consider what happens after a node failure. Ceph will try to re-replicate your data. If you've planned the capacity well, if you paid attention on the slide before, this can succeed, but the system will go into health warn because either it cannot satisfy your crush rule, 2 replicas will end up on the same node, or the system is actually unable to provide a replica count of 3. In any case, the system will still be available. On the other hand, in this situation, the system is incredibly vulnerable. A single disk failure can render your cluster unavailable. With some very bad luck, the system could even lose data. While this seems somewhat contrived, it's far from unrealistic. Planning failure scenarios and stopping halfway can really convey a false sense of security and unwarranted confidence in, say, maintenance situations. Identifying the role network interconnects play in these trade-offs is not easy. The impact on resulting capacity and availability is ephemeral at best. For example, a slower network negatively impacts availability when repair traffic is slowed down due to competing client I/O. Or put another way, the time range in which the cluster is vulnerable increases. In the extreme case, this can even impact safety when repair takes long and consecutive failures hit. So when designing the network topology, it's a good idea to avoid bottlenecks. A fully interconnected network will work best, i.e. a node, especially the OSD nodes, should be able to connect to every other cluster node with the same quality of link. Technology-wise, I really like to recommend 25 gigabit per second hardware, since the technology just has room to scale up, and latency behavior is much better. And this latency will actually be beneficial for your client workloads as well. Another hardware topic, and I admit this one is a bit of a pet peeve of mine, is be wary of RAID controllers. RAID controllers have, often caches built in. They sometimes straight out lie about the hardware that's attached to them, or sometimes they simply can't expose the attached drives as is, or run in what they call JBOD mode. And this can lead to deployment issues, to very confusing performance, or worse actually. They also introduce a single point of failure, which can be very tricky to debug. We've seen a case where all the nodes had all drives, including the OS drive, attached to a RAID controller. And this controller, at least in one node, failed in an interesting way where it would randomly freeze for a while and then come back. This caused a lot of churn in the Ceph cluster because there was constant repair traffic going on. But the node itself didn't report anything out of the ordinary because the OS drive would also just stop for multiple seconds. And last but not least, RAID controllers allow to build very, very fat nodes, so that is very high capacity nodes, and consequently large clusters with a few nodes. Think of our 3-node cluster earlier. You can, put more than a petabyte capacity on these 3 nodes if you wanted to. In the presence of failure, this can, of course, pose serious problems with capacity and subsequent failures. And furthermore, it likely impacts your achievable performance, as the node interconnect is rarely scaled up according to the capacity. So you end up with very high capacity nodes that have too little network bandwidth to talk to each other. Yet another hardware-related topic is that of homogeneous nodes. This is less about trade-offs, rather more a general consideration. On the one hand, having the same number and types of disks in all storage nodes typically makes a cluster easier to manage and easier to reason about when it comes to capacity, performance, or failure tolerance. On the other hand, having identical nodes across the whole cluster can pose a risk. If there's any bugs in the hardware-software interactions, the whole cluster can be impacted. And we've actually seen a case like this where, if I remember correctly, the network card firmware and the switches had, this particular combination triggered a bug that caused a regular reset on all switch ports these nodes were attached to, which made for a very fun debugging process. Or, some of you might have heard about the case about a certain brand of enterprise SSDs consistently breaking after 40,000 hours in early 2020. So this consideration usually seems somewhat esoteric or academic, but only until it's not. And last but not least, 2 recommendations that really should not be necessary, but unfortunately they are. First one is monitor your cluster. The Ceph health status logs, and the Prometheus and Grafana monitoring stack that you get with SUSE Enterprise Storage are great places to observe and monitor your cluster. You usually get early warnings when things are about to go wrong. You can identify potential performance issues very early. So address warnings, investigate slow requests that are reported as early as possible. Don't wait until they develop into bigger issues. And secondly, Ceph is a complex beast and still develops at a very fast pace. It is good practice to at least keep an eye on documentation and best practices. These do change occasionally, even for older releases. That is not the bleeding edge. Okay, I hope this session contains some useful information. Please feel free to contact me with any questions or comments you might have. I hope we really will be able to refine these guidelines in the future somewhat. And one way you can help with this effort is to increase the amount of data we have available from real-world clusters. The new telemetry effort enables you to do this very easily. You can find out more about this on Ceph.io and in another SUSECON Digital session. So let's close with a final quick look or overview of our conclusions. I hope I was able to highlight that thorough planning, specifically before hardware is purchased, can pay off very well. A thorough understanding of the expected failure modes, including subsequent failures, and the impact on usable capacity versus available capacity is important, and consequently, that planning capacity too tightly can very much hurt your availability, or in the worst case, even data safety. Ceph thrives on fast network interconnects and available capacity to re-replicate data in case of failures. So try your best to provide Ceph with what it needs. And last but not least, monitor your cluster. And with that, thank you for attending this session.